Howdy, everybody. So, don't know how many of y'all have been on, speaking of Howdy, how many of y'all have been on Howdy yet since yesterday evening, but I finished grading your homework. And I was thrilled and disappointed. A bunch of y'all did really outstanding on the homework, and some of y'all need some work. So for the ones who need work, open to, trying to find times that we can get together, either here while I'm here on Wednesdays or, via video conference in Dallas, but one way or the other, everybody in this class has got an opportunity, I think, to potentially do relatively well. Any homework assignment you have failed, I have given everybody in their feedback an opportunity, if you failed a homework assignment, to bring that up to a pass grade. So, going to do some work, there's no reason anybody should fail this class. That said, you may have also noticed that I published the midterm exam. I will tell you, quite frankly, you need to start soon, even though you've got a little over a week to get it completed. There's a lot there, and so I would start sooner rather than later on taking that, making sure that you've got it all. Obviously, since it's on Howdy, it's an open book test, so knock yourselves out. What we're going to do today, and depending on how things go today, we may take that into Monday, is that we're going to do kind of a review for the material that's covered in the midterm. I will tell you specifically that state machines and fixed point math are not covered. It will be on the final, but I also intend, at least on the point stuff, to have another class as we get closer to the end to go over that again. And maybe put some of it into homework assignment as well. All right. So, super loops. Somebody help me. What's a super loop? Yeah, just single thread, single program, does one thing. So why are some of these cons, why in a superloop is it difficult to catch an external event? What about a superloop makes some of these cons? You don't have to be specific on that, but what are some of the cons here? You guys have now played with an OS, so you compare and contrast, right? So tell me about one of these cons. Tell me about an issue associated with the con.
So there's, it has to run through the whole code before it receives an event, and there's no priority. So it'll take the full time to run the whole code before it'll respond to any transaction.
Okay. All right. How about the pros? So, you know, it's not all bad on Superloop. What about some of the pros? Why would you, how many of y'all, if I told you today that I wanted you to go out and write, you could choose to do it any way that you wanted to, and I told you that I wanted you to write for a homework assignment program that took an LED on a reference platform and blinked it at 1 hertz. How many of y'all would choose to do that with an OS? Good decision. How many of y'all would choose to do that with a Superloop? Of course. It's one thing, it just does one thing, okay? Now, again, knowing what you know now, if I gave you a much more complex task, like let's say that I gave you the task, and this is not going to be a homework assignment because it's a more extreme example than I'd give this homework assignment. Let's say that I gave you the assignment that I wanted you to monitor an analog input, do a FFT on that analog input on a regular basis, say do an FFT once every 3 seconds, and then take all the frequencies in that FFT, shift them by 100 hertz, and then put out the same signal that you got on the input. So basically decode the FFT. And while you were doing that, I wanted you to process a serial terminal where somebody could type in a different frequency shift amount. How many of y'all would like to do that in a Superloop? How many of y'all think that an RTOS might be a better way to implement that? Even if you're not sure exactly how you'd approach it, right? The RTOS is probably an easier way to break down that problem. So, foreground background systems. What's the difference between foreground background system and a Superloop? Interrupts, okay? So that helps a little bit, right? But it's still not an RTOS. What's the big difference between an RTOS and a foreground background system? Maybe. What's that? The priority system. It's now. Can you reasonably do everything in a foreground background system that you might try to do in an RTOS? Yeah. There's nothing that prevents you from doing everything that you do in an RTOS in a foreground background system. And in fact, the way that RTOSs came about was people sitting around writing foreground background systems and saying, wait a minute, it's got to be a better way to take some of this common logic that I have to deal with in the foreground background system and giving it some basis so that I can handle things on a regular basis. That's how we get to a real-time kernel. So you're going to be asked about characteristics of foreground background systems, real-time kernels, what the differences are, maybe some of the pros and cons of each. Okay? One of the things that you're likely to be asked is, what are the differences between an operating system and a kernel? So if I said that I had a library function that wrote that wrote characters out to a serial port. Separate of the kernel or as part of the operating system? Okay, so why do you say it's part of the kernel?
Because it's a library and normally the operating systems just with task. I guess it could be the 10.
So let's go back a slide here. What did I call TIR here? Okay, so this is one where everybody, TI's poor attempt at differentiating between what a kernel is and what an operating system is that they actually refer to something in their documentation. They have the TI-RTOS documentation, which has lots of stuff, including kernel, and they have the sysbios documentation, which is where if you want to figure out how to sort of task, what priority to give to a task, how to run a timer, how to do a semaphore, all that stuff is in there, what's called sysbios, which is the kernel. So a kernel is the real-time, it's the part, the task scheduling, inter-task communication. Anything that you have doesn't have to do with timing and inter-task communication is part of the operating system. So as for instance, in the example code, the example that I went over with you on Monday for our homework assignment, you know I had to do some configuration to talk to the AD converter. Those were all function calls that had the AD fix, right? That is part of the operating system. It is different than some of the other stuff, the MSP 430ware, in that all of that is operating, all of those things are operating system aware. So as for instance, if you were to use the MSP 430ware, which I think the calls are AD14 prefixes, that is not operating system aware. So when you go to convert, if you're not using the interrupt version of it, when you call to convert, it goes into that conversion routine and it just stays there, and it doesn't let the operating system do anything else. It's just waiting for that convert complete. On the other hand, if you're using the AD prefix stuff, the part that's part of the TI-RTOS, their device drivers, it is operating system aware. And so when it goes in and it's waiting for the A to D conversion to get complete, it's returning control operating system. So another task can function. Now, in the simple stuff that we're doing, doesn't make a lot of difference, but it's important to know that there's a difference between a normal library call and a part that's part of the operating system that is aware that the kernel exists. Okay. Now, there are ways that you can take that AD14 and make it operating system aware, right? You can write your own function that goes off and starts the conversion and tells the conversion, hey, give me an interrupt when the conversion is complete, and have a conversion routine that then posts a semaphore that says, hey, conversion's done. And you can do that on your own, but if somebody has already written that code, why bother, right? So that's operating system versus kernel, okay? It's a very important distinction. And although in most casual conversation, you go out there, you go out and you talk to 100 programmers, and we often use the terms kernel and operating system interchangeably, even though what we really mean 90% of the time is kernel in the embedded world. It's important that you understand the distinction, because when you get ready to go off and make a decision about what kernel to buy, you want to make sure that you're aware that you're buying a kernel as opposed to an operating system. If you're buying an operating system, then you're expecting a different set of features. And so it's important to know the difference. Real time. This is one where, again, where it's just a simple definition, but you really do need to be aware of it and what it means, because the term real time often makes people make bad design decisions based on misunderstanding of the language. So when I say real time, what real time means, as we're talking about with kernels, is that everything happens in a predictable amount of time, okay? The word you want to use is deterministic, okay? It's not that it happens fast, it's that it happens predictably, okay? You cannot, in Windows or a Mac OS, predict how long it's going to take for any particular action to occur. You know pretty much, kind of, sort of where it is, but when you need that mathematical precision of when they're going to occur, you need something that is real time. And you need to be aware enough of the connotations of real time that when somebody presents you with something that they say is real time, that you can ask some intelligent questions to know whether or not it will really solve your problem. I'm going to give you an example that happened to me yesterday. It doesn't have to do with real time, but it does have to do with being prepared to answer questions. So I had a vendor come in. He's an Aggie, nice guy. And he was selling, his company has come up with what they think is the best new conformal coating formula, which conformal coating is something that you either dip or spray onto a printed circuit board to keep water from coming in contact with the actual circuitry, so that if it gets wet, if it gets salt spray, it's fine. And so this guy was making some very interesting claims. One of the things that he claimed was that I could leave my connectors installed. He said, first of all, this conformal coating won't scratch off. It's very permanent, it's micro stuff. And it doesn't affect the operation of your circuits. And he pointed to some examples that he used of circuits that were relatively high-speed televisions in particular. Then he said, but you don't have to mask off, you don't have to keep the conformal coating from getting on your connectors. So what's going through my mind, right, is that doesn't make any sense, because if I've got this thing covering my printed circuit board and electrons can go through it, then it's going to cause current to leak from one pin to the other. So I said, wait a minute, how does that work with the connectors? So what has turned out is that I think it actually is not as durable as what he says, that actually when you use the connector, it scrapes off the coating. But we don't know, because this guy was a salesman. He had the pitch down, he knew what to say, but he also knew that he had to go ask somebody and get me a technical paper to tell me what was going on. If I'd have made a decision based on that, making the assumption that everything he told me was true, then I'd have been in trouble. So what the hell does that have to do with real-time operating systems? Well, one of the things that you're going to have people tell you all the time is that they have real-time Linux systems. Everybody has heard of real-time Linux, okay? There are very few truly real-time Linux kernels, and you have to be able to ask the question about, okay, is it deterministic? Great. Tell me about interrupt latency, not a term that we've talked about in this class yet, but tell me about interrupt latency, okay? Tell me about your priority system. Tell me about how you do your task switching. Tell me all of these, because now you can ask some specific questions that the people who run to you aren't going to be able to answer, but they'll be able to find you a white paper so that you can read and see if this truly will work for your application. Because if you need real time, if you need determinism, you need it. Okay, you can't get along without it. So, hard real time versus soft real time. Tell me the difference. Right. Very good. So we talked about determinism. Fastware is not always real time, right? If you can't predict if you can't predict when it's going to react, it's not deterministic, no matter how fast it is, right? If I make a CPU fast enough, it's going to feel like things are happening quickly. That doesn't mean it's deterministic. That doesn't mean just because things are happening fast doesn't mean that I can necessarily use it for doing things like digital signal processing, okay? That's one of the reasons that when you look at a Windows machine, some of the low frequency stuff they can get away with doing the actual processing in the machine, but for the most part, they have dedicated ICs that are taking care of the stuff that is hard real time, like sampling analog inputs and that sort of thing. Okay. Two types of kernels. What are they? And preemptive and cooperative. What's the difference?
Preemptive, when a higher priority is triggered, it'll go to the highest priority.
Does a cooperative not go to the highest priority?
So when an interrupt is triggered and preemptive, whatever task it's on doesn't necessarily get to go after the interrupt happens.
Bingo.
It's going to have a higher priority after that. Cooperative, it just goes back to the task it's on, then it might go to a higher priority afterwards.
Well, it will go to the higher priority, but only when the current running task says, oh yeah, you take it, right? So there are actually advantages and disadvantages to both, right? There are reasons that I might not want my task to get stuck being constantly interrupted, that I might just want to let it go complete. On the other hand, there's some beauty to being able to pop out, you know, because an interrupt happened, something changed, and take the next highest priority task, which, by the way, is almost always a task that was made ready by the fact that you had the interrupt occur, right? Because nothing else is really happening if it's not associated with an interrupt. So let's think about it. So I've got task A. Task A is sitting over here and he's doing things. And let's say that he decides to post a semaphore, right? So task A posts a semaphore. That post actually can give control to the operating system, and the operating system say, oh, since you posted that, this guy who's a higher priority than you was waiting for it, we're just going to let him run, and it doesn't return until that's finished. That's a very reasonable way for a cooperative operating system to go. If task A is going along and he does append, waiting for another task, if that task is not running yet, right, we're just like the operating system, we pick the next highest priority task. Both of those get control back to the operating system, not associated with an interrupt. The only thing that a cooperative kernel will ignore is that an interrupt occurs, right? That interrupt sends something into a mailbox, puts something in a queue, or does a post to a semaphore in that interrupt. And at that point, if it's a cooperative, it simply returns until the running function feels like the running task feels like he's had enough of the kernel and he's something to go back and talk to the kernel, return control, whether it's a wait or whatever. In a preemptive system, that means that it's to go pick when the interrupt happens, the operating system reevaluates on the return from interrupt. Who needs to run? What really makes that cool about preemptive operating systems, every preemptive operating system on the planet Earth, and in fact, all of those in orbit as well, and those of us in free space on the way out to places unknown, if it is a preemptive operating system, it will have heartbeat timer, a system tick. Okay. Now it turns out systic is a very ARM processor specific terminology. A lot of folks call it a heartbeat timer, but if you're in the ARM world, it's always systic because ARM processors actually have a very specific timer built into them that is good for absolutely nothing except generating system ticks. It's the most worthless timer in the entire world unless you need a systic. And then it's really versatile. It does exactly what you want to do it every time. So that's important to know when we start talking about timing, because what that means is that when I do a timer, right, I know that no matter that, as long as I have a high priority, when that timer expires, I'm going to, with a preemptive kernel, I'm immediately going to go off and execute that thing that happens on the timer. Does that make sense? Okay, priorities. Priorities just tell the kernel which way they need to. If in the TI kernel that we're using, if I have a task that's ready that is priority 3 and a task that's ready that is priority 4, which task runs first? Which one? That is correct. Okay, so creating tasks. There are multiple steps. Turns out that, with the exception of the params, the initialized params call that is kind of unique to the TI kernel, pretty much every operating system in the world requires you to do the same basic thing to create a task. You create a stack that the task is going to use as his stack, and you create a task control block. In this case, what TI calls their task control block is the task struct. Okay? You got to have those two things, right? The operating system absolutely needs to, the operating system doesn't know that there's a task to execute without task struct, right? Doesn't function to execute when that task is active without a task struct. The operating system also needs to know how big the stack is. Why do you think the operating system cares how big the stack is? Yeah, because one of the features that almost every operating system allows you to turn on at some point is something that every time a task exits, to measure the stack depth, how far down that stack has been consumed. And in fact, there are tools with the TI RTOS that we can turn on that let us see how deeply we have gone into a particular stack. So you can look and say, hey, I've consumed 23% of my stack. I've consumed 98% of my stack. By the way, when you've consumed 8% of your stack, it is time to make a bigger stack, okay? You always want wasted space on a stack because there's always that one more interrupt function that you forgot about. There's always that one more if statement that does a function call that you only execute once in every 3 moons that's going to need a little bit more stack space. So when you get up above 70% stack usage, it's time to make your stack a little bigger. Not a bad rule of thumb to think about. Not on the test, though. Just good to know. For the TI-RTOS on the MSP 432, 512 bytes is a really good place to start. Now, anybody want to guess why we had to go up to a 2048 byte stack when we did the when we're doing graphics routines? So the libraries are big, but what does that mean? You know, are you talking about big code space? What makes them big? Okay, so what about the complexity?
What's the resolution of those? Like,
I think it's 128 by 128 characters, and I believe it's 8-bit color.
well, just from my minor experience, 369 having to program that LCD screen, which is turning on a single section of stuff.
Yeah.
To control 128 characters, not even including pixel size of each of those, and everything required to actually with the vector to place it on the screen in the right spot. I'm pretty sure that will fill up a lot of that space just to hold that library with the calls and everything.
Okay. So it takes up code space. It's not stack space, though.
No, it's not that big. Then I guess it's just making sure those where everything is. Then just because you have to, like, yeah, you have the library calls, but you have to remember where everything is to understand it on the screen.
Okay. So I'm going to help you because you guys haven't gone through these libraries. I've actually some time looking at how they wrote the libraries because they're frustratingly slow. You guys probably noticed that. First time you run your function on screen, it's like, is it running? Is it running? Oh, there it is. I see a pixel. So here's the way this library works. So two things. You've got this graphics context that it creates. So that graphics context, which you never declare in the stack, you always do that at a global level, right? What that is, among other things, is that it has a bit-for-bit map of the whole screen. So 1 byte per pixel, 128 times 128, which is a bunch, right? That's 1024, right? I think that's right. So let's say that you want to draw on that screen, and you're using the transparent mode, which is probably the one that requires them to write the bits this way. So the transparent mode, when you write onto that display, what you have to do is that you have to change the color only of the pixels that you're actually manipulating, right? So you have to know which pixels I'm turning on, but you don't mess with the pixels that are off. You're only messing with on pixel. So you have to be able to get that out of what is being displayed, and that's cool because you've got that in memory. You can't read the display. This particular display is not, although it can be read, it would be slower than Christmas, and it's not wired that way on our reference platforms. So you can't read it, so you have to have this memory map that we have in there that's the image, and you have to go off and compare it, but you also have to go off and write it. So when you get ready to write, say, a word, you have to go out and you have to figure out, I'm at this spot right here, and I have to go pick another bitmap that tells me which bits to turn on, and I have to set all those bits. Well, what happens is that to keep the code from getting horribly complicated, you have to create a buffer that's as big as what it is that you're going to be putting on the screen anyway. And because it's further complicated by the fact that the display takes stuff serially, every row of pixels has to be 128 pixels long. You can't do just the front couple of pixels or just the back couple of pixels. You always have to paint a full row. So what that means is that I have to make these big buffers every time I get ready to write something out. And if I write characters that are in a large font, that means that I've got more rows that I have to keep. And so that's every row of pixels is another 128 bytes I have to shove on the stack while I'm doing my manipulation. Okay? So that's really cool. So right now, the way that most of us wrote our homework assignment, right now that particular method of doing things is that in an individual task for, say, the button, to write that line for the button, we're actually making a call to the graphics routine in that task, which means that task has to have enough stack to support however much stack the graphics routines are using, right? Can we think of an architecture that would reduce that stack space? If I want to save some stack space, can we think of an architecture that would reduce that?
Like the overall stack space or individual stack space?
Individual stack. So I want tasks to be able to write to the screen, but I don't want them to have this enormous stack. How could I change my architecture to do that?
Smaller buffers, and then it gets interpreted in that task, and then what it wants, instead of having to actually, like, you make a string buffer, and then you put that string into that task, and that task turns that string to what it wants. It's a graphical construct.
Right. So what we would do, if I were going to re-architect, that's great. That's exactly what, and I'll rephrase this. If I were going to re-architect this graphics library to be compatible with an RTOS, I would have a task display, or a display task that does nothing but display. And what that does is that task will sit there and look at probably a mailbox, either a mailbox or a queue for, hey, what do I want to display next? And that would have as packed in information as I can. So if I want to be drawing text, it would have the row and column that I want to start the text at, and it would have maybe the color of the text. You know, those are just a few bytes, and the text itself, which again is only a few bytes compared to how many pixels it's going to take up on the display, right? And I have it sit there wait for that. It might also interpret something else as draw a box of this particular color at these coordinates. Again, we do that all with relatively small chunks of memory, right? And we can make the operating system do that. And we could write it like that. And then personally, I would go further to say, I'd get all that stuff, I'd create 2 copies of my, I'd spend a little extra memory, keep 2 copies of what the display looks like. And when somebody told me to display something, I would create the new thing while I'm keeping what's already there, and then I'd compare the two going through row by row and only spit out what got changed, at least those rows. That would make things go a lot faster. We'd all think that display was a lot cooler than it really is. Okay, but at any rate, so stack size is very important, something that you need to be thinking about anytime you're in an RTOS. So specifically for the TI RTOS, you have this structure, task params. There are a lot of things in there, but you have to specifically manipulate on your own arg0 and arg1, the task priority. By the way, does anybody know what the RTOS does when you initialize task params if you don't hit task priority? What priority would it be?
0.
Okay, so let me ask you. Okay, so let's talk about this for a second. So there is a thing called the idle task that's part of the operating system, and it is priority 0. I'll go ahead and just give you the clue because I've read the manual about 6 times. Turns out that that is the only task that can have priority 0. Okay. There's some good architectural reasons for that, because that particular task is what you use to determine how much free time the CPU has. And if you have somebody else that's taking up time, it'll throw those numbers off. So task 0, it can't possibly be priority 0. How many priorities does the TI kernel support? How many levels of priority? How many? So it turns out actually with the ARM architectures, it'll support up to 30, through 31. But you're right, with the MSP architectures, it supports up to 15 priority levels. So would it make sense for the operating system to pick, by default, the highest priority level? Nah. I can see a really good argument for picking the lowest one, which would be 1. But in fact, what they did was they got out their high-dollar TI calculator. They did a divide by 2 and rounded the result. And so priority 7 is the default priority, right smack dab in the middle. Now, can I have 2 tasks that are same priority? Absolutely. So if I have 2 tasks that are the same priority, that are both made ready to run at the same time, which one is the operating system going to pick?
I mean, isn't that what's it called? It's when you don't know which one's actually going to happen. It's like something.
It's called random. Yeah, so the operating system might, it is undefined actually. The operating system might pick the first one that, the first task that pended on whatever it is that became available. It might. It might pick the one that got created first. It might pick the one that got posted last. It might pick the one that got created last. What we don't know is we don't know the guts of how the operating system goes in and makes that particular decision, decides who's next to run. And they're not telling us because they may decide to change that at some point in the future. So what you know is that you don't know if anything has the same priority. Now, again, same priority. What that means is that at the same interrupt time, because we're a preemptive kernel, right? At the same interrupt time, 2 tasks have to be waiting on exactly the same thing and become ready and have the same priority for that to even become an issue. It's a pretty unlikely thing, but it's good to be able to talk about it if you ever need to. And it's a good excuse, by the way, to always try to give every task that you make a different priority. Now, the MSP 432 has enough memory in RAM that if you don't, if everyone is not a graphics routine, if everybody's like at 512K, you could conceivably have more than 15 tasks. That's a possibility. But I will also tell you that it might be for how much power you have in MSP 432. It might indicate if you have more than 15 in a 432, it might indicate that you have overthought the problem and perhaps created too many tasks. Okay, you also have to have a pointer to the stack, and you have the stack size. Oh, anybody remember how much, if I want an operating system to remain deterministic, what is the absolutely largest percentage of CPU cycles that can be consumed by the tasks that are running, by things other than the idle task? What'd you say? Okay, so The correct answer is 69%, but 60 is close enough, okay? And in fact, in practicality, I think I told you in earlier lectures, you know, once you get much beyond 50%, because this is all based on math that isn't anyway, once you get up to past about 50%, things start getting a little flaky with any kernel, which means that we're always oversizing our CPUs, right? But I will tell you, most foreground background systems that I've seen, and every superloop that I've ever seen, the CPU spends a huge amount of time doing stuff that doesn't need to get done, right? Sitting in loops waiting for things to happen. Okay, so I will, on the midterm and on your final as well, ask you to actually show me some code, write some code that is specific to the TI. But I'm going to ask for chunks. I'm not going to ask for complete working programs. I'm going to ask you, what's the code that you need to execute a particular thing? I will always, unless I tell you that something is defined in the question, I expect you to create the declarations as well that it takes to make whatever it is that I've said needs to happen. So what you need to know about for a task is that you have to allocate the task control block, you have to allocate the stack, you have to do the params init, and although I didn't show this example, I would expect you to actually show me the declaration for the task params variable. You need to set up all the arguments and do a task construct. If I ask you how to do it, with the exception of adding the declaration for task params, that's exactly what I'll see. Okay? And as a rule, these won't be I'm not going to be looking for compliance with coding standards, really, but you won't have indentation and stuff in most of these questions. And quite frankly, I forgive spelling errors and that sort of stuff. Things that the compiler would catch and would be obvious, I don't care. Okay? What I do care is that you show me that you understand how to create this stuff, and that, you know, with running a compile cycle and correcting the errors that generates, that you can get it done. And obviously, if I ask you to create a task skeleton, it might look like that. Reentrant functions. So, what makes ls digit non-reentrant?
Saving the value bar into that function.
Mm-hmm.
If it's interrupted, the value contained and it's not that variable is not how do you say
It's not protected.
protected, but within the scope only of that function.
Right. Other folks can mess with that value. Okay? Cool. And I'm not going to talk about the reentrant function, because if you don't have any of the flags that it's non-reentrant, what makes the print fifth non-reentrant? Has a static variable. Absolutely. Okay. And we taught str tote. Okay. Ask you to do a timer sleep, or to do something on a timed basis. That's the function that we're going to talk about. It's task sleep. Task sleep. You guys have used task sleep a lot. The parameter that we pass to it, what units is it in? You said milliseconds. Anybody else want to venture a try at this? Timer ticks. Okay? So the default configuration, if you don't mess with anything, for this particular kernel is 1 millisecond timer ticks. Okay? But that's not necessarily true for everything. Okay? It is something that you may actually choose to tune after you see how much real time you have available, right? So let's say if we have a really busy real-time kernel system, and we're out cranking along doing our thing, and we use the diagnostics because things aren't happening kind of like we expect them to, and we find that only 30% of the time is available for the, let's make it worse, 10% of the time is available for the idle task. So our RTOS is consuming 70% of the CPU, or 90% of the CPU. 100 minus 10 is 90, right? So we're consuming 90% of the CPU with real work, and that's not working out with 100 millisecond with the 1 millisecond interrupts. If I don't have anything that the determinism has to be with 1 millisecond granularity, I can save a huge number of CPU cycles by not waking up every millisecond, because what happens when that timer tick hits, interrupt generated. So the first thing that happens is everything gets pushed onto the stack, right? So that's going to take, depending on the number of registers in the CPU, that's going to take 15, 20 instruction cycles that you then now have to get back when you do a return, once you pop it all off the stack, right? So we have the interrupt. We've shoot up 15 instruction cycles for that. Now we have to take a look at what caused the interrupt, okay? So that's going to take some instruction cycles. Then we have to go say, okay, which things within the operating system might have been dependent on that particular activity, okay? At least I'm going to be counting down some timers, right? So I'm going to count down the timers. I got to go look at all the timers, count those bad boys down. I have to see which ones have expired. Then I have to go see, hey, is there any stuff that needs to be run? No, there's nothing that needs to be run. Well, that consumes a fair amount of CPU time right there, right? So if instead of millisecond granularity, I could live with, say, 10 millisecond granularity, just to interrupt 100 times a second, you can take a huge load off my CPU. Furthermore, if I've got a power-dependent system, reduce my power consumption, because anytime that I'm in the idle task, I can put the processor to sleep until the next interrupt, right? I save a huge amount of time by cutting down on the frequency of my system timer tick. Here's what that means to you. When you're using the system timer tick, don't assume that it's milliseconds. Have a pound defined someplace that you can set that says, this is the number of ticks per millisecond that I have, and every time you call that tick, recompute what it is. That way, if later on, when you're reading your code and optimizing it, you decide that you can live with a different timer tick, you can fix that without having to go find every one of your timer calls saying, okay, what's that one, right? This is stuff that you can take care of when you're writing the code initially. So let's talk about semaphores, and then we will stop for now and know that I've got a lot more slides than this for the review, but we'll stop at semaphores. Okay, so semaphores. If I've got a semaphore that I'm using to signal whether or not an event has occurred, will I be using the value 1 or 0 to represent that the event has occurred? So, okay, so let me phrase it a different way. If I am doing a pend, with a wait forever, what value does the semaphore have to have for that pinned to return? 1? Is that what you said?
Yeah, because it goes to 1, then you pin, then it goes back to 0, but it has to be 1 first.
Very good. So a 1, a non-zero value means that if we're looking for a pin that represents an event, a non-zero value represents that the event has occurred. Okay? Now, if I'm using a pinned, this may be a little bit more difficult to think about, but we'll try it anyway. Let's say that I'm using a pin to control access to something, right? Or a semaphore to control access to something. So I only want one function at a time to be able to access a particular I/O port. And so before I access the I/O port, I do a pinned on that. I do a pinned on a semaphore associated with that I/O port. What value in the semaphore indicates that that is in use? So I want it, when I do the pinned, I want it to pinned until it's no longer in use. So 1 means that it's in use. Right. Okay. That's good. That's one that I even scratch my head about when I'm thinking about it, but it's kind of sort of the opposite, right? So what's the difference between a counting semaphore and a binary semaphore? So explain that. Mm-hmm. Mm-hmm. Okay, so that's sort of correct. So it does, every time you do a post to a counting semaphore, it will increment, and it will increment beyond 1. So if I do 26 posts to a binary semaphore, it still just goes to 1. But if I do 26 posts to a counting semaphore, it'll go to 26. And a counting semaphore is, think of it as a piggy bank. Okay? And when I do a pinned on the counting semaphore, basically I'm going to the piggy bank and seeing if I can take a coin out of the piggy bank. Okay? So as long as it's non-zero, I'm going to take the coin and return. And there's now 1 less coin in the piggy, right? Anytime I go and I put a coin in the piggy bank, we just get more coins there. So the next guy who pins has a coin. Eventually, the piggy bank, we don't have enough folks depositing and everybody's pulling out, eventually the piggy bank is empty. Okay? When it's empty, then I do my pinned until somebody puts another coin in the piggy bank. Okay? So, good to not counting semaphores. They are handy for things like the example that I gave you, which is not a great example, but it's an example that's pretty easy to understand, is that if I have an interrupt routine that is putting characters off the serial port into a buffer, in my interrupt routine, every time I put a character in the buffer, I can post to that semaphore, right? And then when I have the task that's pending on that semaphore, waiting to pull a character out of that buffer, when he does, he can check that semaphore each time to see if there's a character to pull out of the buffer. Okay? And so now, and then when there's no characters in the buffer, when he does that pin, he just pauses. Or he can sit there in a continual loop until it decrements down, you've captured every character out of the buffer. Not the way, by the way, that I do a serial port. I do that probably with a mailbox or a queue. But it's a way to conceptualize the sorts of things you might do with the counting semaphore. And quite frankly, you need to know about them because you may encounter them at some point in time, but the odds are you're not going to have very many occasions to design with the counting semaphore. Yeah.
In that example, we're talking about with the knowing if the serial port is being used or not, like which one is being used or not. If you have like, let's say 5 serial ports, and you wanted to keep track of like all of them were in use or none of them used, would you think a counting semaphore works there? Or would it, because I know it wouldn't specify exactly like 4 would mean that these 4 are on, it's that 4 are being used right now.
Depends on how you wanted to architect your system. And so, yes, that's a pretty common use of counting semaphores, that if I have a limited resource, that I can go out and I can, you know, if let's say I've got 5 serial ports, I can go out on initialization and do 5 posts to the counting semaphore, and every time I need a serial port to go off, I pinned on that, and if the pin turns, then I know that I've got a serial port available. The problem with that logic is that you still have to figure out which one you're going to use, and that is, you don't get with the counting semaphore, you don't get which number you got. You just know that the semaphore got posted. It's a really primitive kind of a thing. So there might be other ways that you want to handle that. But let's say that you wanted to simplify the initialization of your serial port, right? So I got a serial port, I want to simplify it, I don't want that to be OS aware because I've got a library call. Then one of the things that you could do is that you could use that counting semaphore if there was even a chance that I was going to get that serial port. And then I could go and I could try each serial port to see one was available. That's certainly a way that you could use the counting semaphore, so that you don't waste your time when you're not, when there's not going to be one ever available. Okay, so let's go ahead and we'll stop here. For today, we will pick up again on Monday, finishing up the review. That doesn't mean you shouldn't try to start looking at the midterm and getting what you can get and going back and rechecking it since there's a bunch there. Cool. All right. Have a